For this video, I wanted to go over a little bit of kind of the basic ML framework or pipeline. There's a set of elements that we talk about over and over again, a set of vocabulary that we use over and over again, a set of components that are very often involved in models. But because they're not exhaustive, we generally don't take the time to sit down and explain them all because mathematicians are terrified that they might get something wrong. And so they never try to explain things in like clear, concrete terms. They always try to be as precise as possible. And if we were being as precise as possible, not all of these items will appear in every machine learning model. The exceptions actually sort of swallow the rule. There are more exceptions than there are actual cases of this model. But this model will give you kind of a vibe of what we're doing when we're using a machine learning approach. So the first thing that we would do is we're going to start with kind of a statistical approach. So I like to take this. So the first thing is we have sort of a statistical intuition. And the statistical intuition I like to put as um, everything screwed. And because you don't really know what number it is, let's call that variable. Right? So everything can be described by, of course, let's start with the most popular variable of all time, x. Right? So very often we'll have a set of data, and we'll call that data something like x. Right? So then, and x, it could be let's see, something like this. X is a list of numbers. So everything can be described by a number. Second has sort of a corollary to the first one. Relationships, and of course, I call these relationships. So you might have something like equals y, which means that for every x we plug into this function, we can get out a prediction for another variable that is related to our data, to our x's in some way. Right, so this is a very basic statistical intuition. It's very straightforward, and immediately we can start building out machine learning model from that. So on the one hand, over here, we know that what we're going to start with is some data. Now, I think most people are accurately kind of picturing sort of like a spreadsheet, right? Where we have a bunch of rows, have to be black. We have samples. Another way of saying samples, you might call these observation. Means the same thing. They might be measures. Call them measures. Or if they're in time points. So those are our rows. And then for our columns, we would have what you might call signals, or variables. So you have a list of all these different variables, and you kind of make this it's a little spreadsheet like this, right? So we got over here, we've got all the times that we measured, and then here are all the things that we measured, right? Very common framework for data, very useful thing to have in your head. but it's incomplete because all kinds of things can be data. So, so far we've been talking about data as if it were this flat sheet, but you could have lots of different kinds of data sheets, right? That, in this kind of nice 3D cube or projection that keeps track of a relationship between more complex multivariate data. You can also have, all kinds of things can be data. I noticed earlier in the thing, I had these awesome stickers, so I decided to use them. Um, you know, audio is data, right? It's frequencies, and photos are data. They're maps of pixels, right? So every pixel on your screen has a data value. It has a value that denotes its color and its luminance. Sometimes it has multiple values that denote its color and luminance, so that you can have a big array, that looks just like this matrix up here, where the first one is the very upper leftmost pixel of the screen, and then the second upper left, one step to the right pixel, two step to the right pixel, three step to the right, and as you go down the column, so you have this array that describes pictures, right? You can even have more complex stuff, touch sensors on stuff. All kinds of stuff can be data. So data is a really big category, and will often have these very complex observations. It's important when you see a bunch of data to think in your head, okay, what are the numbers? What are the variables that I'm describing? How many samples do I have? How many pieces of data do I have? How is it written down, right? You should always be able to get it back to some kind of picture of something that looks like a spreadsheet in your head, or that looks like an array, a matrix of data. That's going to be a very important representation of the variables that we're observing that we're going to use over and over. Again, not universally, but in almost every case, having a spreadsheet in your head is a really good way to kind of get started. All right. So that's our X. So that's our left side, the model, our inputs. And then way over here on the right side, we also know where we're going. So we have a Y, which is our outputs. Maybe our targets. Yeah. Very often in this case, we will have a prediction that we want to make. Maybe you want to guess something accurately. Maybe we want to make match pictures to categories, something like that. So we have a set of an ordinal set of labels. Maybe we have, maybe we're just trying to recapture the data, regenerate the data. So our outputs, we just want to match our inputs, right? So our X's and our Y's are the same list of numbers, and we just have a model in between to match them one to the other. But this is where we're going. This is what we kind of want to predict out, right? And so we have on the, now we know the endpoints, right? We know where we start, where we're going. So I want to talk a little bit about what's in the middle. So in the middle, and I'm gonna, it's got a little bit smaller. Move all this over. Radio. Okay, so in the middle here, we then have a model. And a model is the idea of a model is that this is a piece of machinery. This is an algorithm. It is a function. It is uh, a representation that converts X to Y, right? So it takes Y, X as an input, and it gives you Y as an output, right? Or its best guess of Y as an output, right? Very simple model could be something like f of X and some parameters theta gives you Y, right? That is a very simple model, right? Now, in fact, this model is a very general way to write down the kind of machine learning models that we have. Very often, all we're trying to do, all of the fanciness of what we do goes into figuring out exactly what this function here should be, and all of the wizardry is in figuring out this function and these parameters. Right? You're given the X, you're given the Y, and you have to figure these things out. Occasionally, you'll actually be given the model and the parameters, and you have to figure out X and Y, right? Similar idea. But that is what's going on here. You're given something, uh, you're constructing this model that converts your inputs to your outputs. Okay. So now there are a few things to go about how you might do that. And this is a really good time for a machine learning joke from XKCD. This is one of the most famous comics about machine learning, and it is 100% accurate. This is your machine learning system. Yep. You just pour the data in this big pile of linear algebra and collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. Right. That is actually really accurate and shockingly accurate for how these models work. Let's talk a little bit about what that means. Okay, so let's start on this side with the data. So one of the first things that we're going to need to do when we get some data is we're going to want to do some pre-processing, right? Pre-processing just means converting the data to a form that's more usable by our model. If we're working in images and we have kind of a color map, we may need to convert that to grayscale, right? If we're working with maybe we have a list of labels for something where we have cat and dog pictures, we have a list of cat and dog labels. We want to convert everything to a number, right? So we want cats to be ones and dogs to be zeros, something like that. So doing pre-processing, there are other things that you can do in pre-processing. There are whole algorithms that we'll learn that you just apply to the data to make the data more consumable by the model, more workable for the model to use. And we can add in a bunch of those steps in pre-processing to make our models more accurate. So it's a whole big area, but one of the first things we do is basically just change the data around, tweak the data around, apply some functions to the data to get it to make it more conducive to use in our models. All right, the second thing. Okay, so now we've got data that we can actually use, and it's time to go to the next step here. The next step is usually, and very closely related, the objective. Okay, so these are two closely related concepts that have to do with how you are actually going to make changes to your model. It's kind of funny that we have to talk about them because we haven't really applied the model yet, but they're the, this is kind of where you need to think of them in the pipeline, I think. So the learning algorithm is just, what do you do? What is the actual procedure that you do to make updates to your model, right? How are you going to change your model, right? And then the objective function is a measurement of how correct or incorrect your model is. In the stirring the pile of linear algebra thing, it's like if the answers are wrong, that is measured by the wrongness of the answers is measured by the objective function. So we're going to take our pre-pressed data, we're going to pass it through the model, right? And we're going to figure out what the mismatch is between the model's guess and our data. And we're going to apply a function that measures that mismatch. So the objective function here, that's sort of the, oh dear. This is the how wrong I function. This way, because this is fun. Okay, so this is the how wrong am I function, right? Now, then the learning algorithm is going to this is sometimes you might hear it's called the cost sometimes, right? And the learning algorithm is going to consume this cost, right? And it's going to figure out how wrong the function is, how wrong your guess was, and it's going to make some changes to the parameters. So the learning algorithm specifies how we change the function, the function and its parameters of the function in response to measuring a measure of wrongness that we get from our objective function. Okay, so so now we have a kind of an iterative procedure. We can take a data point, pre-process, put it into our model. Model makes a guess. We get out this objective function. So we have this little loop going on here to get a measure of how wrong it is. The objective function passes that over to the learning algorithm. It updates these parameters. Now we could try again. We could try again. We could try again. We could try again. And so we're getting out these guesses of our target outputs that are hopefully getting increasingly good as we go along if our learning algorithm is working. But in order to measure how good our guesses are, we need something else. We need something that comes over here, and that's metrics. So in the objective function, we're kind of measuring how far off is our guess. But this is a statistical framework. We make a lot of guesses, right? What if you get one guess exactly right and every other guess wrong? What if you get half of the guesses sort of right? Is that better? Is it better to be bullseye on one and off on other things? Is it better to be kind of right all the time, right? Measuring the distance between our targets and our guesses with our objective function isn't enough. We also need some sort of metric that measures kind of how good our model is doing overall. Common metrics are things like, actually, have a common framework here. Speaking of doing things that way, let's move this up a little bit. Actually, just realized. Model metrics and our targets, right? We have a way to clean these. We can kind of once we've got a bunch of measures coming out of our model, now we need to measure it. So common things are things like um, how much does the model guess right? Precision, right? This is a measure of how much the model guesses right divided by how much it gets correct answers in general. How specific are its answers for correctness? Right? Does it tend to be both accurate and not make a lot of false positives? So you have a a number of measures that you put into your model to evaluate kind of the model's performance overall, right? And that allows you to compare among models. You can compare which model is giving me the best accuracy, which model is giving me the best precision, right? And then finally, we have this data that comes out. We have these targets. We have this list of guesses. We can measure how good our model is based with our objective function. We can measure how good it is with our metrics, and we have this sort of total pipeline that we can pass our data through. Again, the this is not an exhaustive idea about machine learning. Not all machine learning pipelines work this way, but this pipeline underlies a lot of analysis. What you're going to learn from this point forward is pretty much not um, ways to set things up, but more so specific details of this process, right? Specific problems. How do I deal with specific kinds of data? What's an appropriate learning function for this data set versus that data set, right? What does it mean to have good accuracy? How can I evaluate my model? What are some common things that go wrong? There, one of our early classes, we talk about a base rate problem where a model will seemingly give you very, very good accuracy by uh, without learning anything at all about the data. There's no learning going on. The model is just guessing. It's like a coin flip, heads and tails, and the model's just guessing heads all the time. So it never actually makes any predictions. Your model isn't actually doing any work, but it seems to be about 50% accurate on a coin flip. So you need to learn kind of the deeper context in which these systems work. But I really think that starting out with this kind of framework in your mind, that very often, gives you something to grasp onto. Start thinking about like, okay, when I say data, what do I picture, right? So I've been talking about it in a spreadsheet format, right? Did anybody picture, you know, data like this on a set of axes, right? Because that's data too, right? This is our target and this is our input, right? Did anybody, when I said model, picture a line like this, right? Because this model is of the form, this line is of the form y equals, say, beta x plus some, let's call it theta 1 and theta 2, right? Plus a couple of parameters, right? So this linear model, right? That's also a model, right? The 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 basicness of this, we can apply this with a simple linear model like this, and our early classes will be on that. But as we go on, we will learn more and more elegant things to do with these simple tools. But it's good to start out with this basic frame. This is the basic idea, the basic, statistical idea that we're doing. And I'm going to show you how to apply it in ever more spectacular circumstances, ever more spectacular data sets, ever more spectacular outcomes, ever more clever learning algorithms, ever more subtle objective functions. And this basic pipeline is what we'll use again and again. You should be able to understand it. You should have mental imagery for every single piece of this. You should have the ability to open up a code book and write up, stuff that manages and flexes data around, stuff that applies learning algorithms. You should be able to take, both to plot and just to iterate through all your data and kick out the answers. Right? You should be able to do all of that. That is all part of learning this basic framework. right? And so starting from this basic framework, this is something that I recommend if you don't kind of have the engineering and coding experience to deal with this, or you don't have the kind of statistical background to think about things this way. This might be a good area for review. But if everything, I don't think anything here is particularly outrageous for folks who are coming in from FA and from the linear algebra uh, undergrad statistics classes that feed into this class. So this part of it should be pretty straightforward. And I really just wanted it to be sort of a preamble so everyone would know, okay, I know all this stuff. This is the sort of stuff we're working with, but I'm about to apply it in new ways. All right. Thanks. See you in the next video.